Good morning, students.
Good morning.
Welcome to all in this next session of fluid mechanics. So far in the fluid mechanics, we have already discussed the basic fundamentals: fluid statics, fluid kinematics, and fluid dynamics. Now we will start the application of those four fundamentals, that is various type of flow. Okay, but before starting that, I want someone from you to give a brief introduction of previous lecture. So can anyone come?
Good morning, all of you.
Good morning.
So, in previous lecture, we are discussed about the equation of free surface in vortex flow. Equation of free surface in vortex flow is described as a periodic chain, which is that Z is equal to V square or V square upon 2G or omega square R square upon 2G. Then we are discussed about the fluid flow analyzed by Reynolds transportation theorem. Reynolds transportation theorem gives the two statements. First one is the control mass and second one is the control volume. Control mass as like term indicator control mass. In this state, fixed mass of the fluid element in the fluid analyzed, and the conservation equation are written. And in control volume, and the arbitrary fixed volume located at a certain place. This property may change from time to time. As like equation del n upon dt is equal to dn upon dt. Control surface is bigger, small n, rho v a dv. And then we are discussing about the physical interpretation of Reynolds transportation theorem. In this rate of change, the first term indicates the rate of change of property. Rate of change of property is also called the rate of generation of property. And rate of generation of rate of if the turn is mass, then rate of change of property is zero.
Thank you, Shivu. So our today's lecture is viscous flow through pipes. This is the first topic of our third unit, viscous flow through pipe. So our objective for today's lectures are: first, the introduction of viscous flow, then we will determine the shear stress distribution, velocity distribution, average velocity, and the pressure drop in a pipe due to viscous flow. So our objectives clear to you?
Yes, sir.
You can write down the objectives. Introduction to viscous flow, then determining the shear stress distribution, velocity distribution, average velocity, and the pressure drop in a pipe. And the reference books for this topic will be Hagen Poiseuille, Sengen, and I have taken down some through NPTEL also. Okay, so let's start. So viscous flow. Before starting the viscous flow, first we will focus on internal flow. Now, what is internal flow? So previously in fluid mechanics we have studied about the various types of flow, like steady flow, unsteady flow, compressible flow, incompressible flow, uniform flow, non-uniform flow, turbulent flow, laminar flow. Okay, so it is another category of classification, that is internal flow and external flow. So internal flow and external flow depends upon when a flow is forced over a surface or inside a conduit. Conduit means a duct or pipe. If this conduit is completely filled with the liquid, then only it is known as internal flow. Otherwise it is external flow. Okay, this you can also understand with the help of closed channel flow and open channel flow. So closed channel flow is internal flow when the conduit is completely filled. But when the free surface of liquid is in contact with air, then it is known external flow or open channel flow. Now if you take the example, so see the example of blood. So blood which is flowing through our veins, it is an example of internal flow because completely filled. Veins are completely filled. Similarly, flow of water. So flow of water through tap or pipes, it is also an example of internal flow. Whereas you have seen the large sewage pipe in movies. So many movies you have seen the hero is going inside this sewage, and so large sewage pipes are there, but only a portion of those pipes is filled with water, liquid. Okay, so it is not an internal flow. So are you clear about internal flow or external flow?
Yes, sir.
The possible condition for internal flow is conduit must be completely filled with water. Okay, now the internal flows. So we have two types of internal flow. First one is viscous flow or laminar flow or turbulent flow. So it is viscous flow and turbulent flow. Okay. So first in this unit we will cover only viscous flow. Okay. So viscous flow through pipes. So now you have understanding about the internal flow. So viscous flow through pipes. The viscous flow, the characteristic to flow is given by scientist Reynolds. Reynolds given criteria that which flow should be laminar, which flow should be turbulent. So if the Reynolds number we know from previous lecture, what is the value of Reynolds number? Is rho v d upon mu. It can also be termed as the ratio of inertia forces to the viscous forces. Now, if the viscous forces are dominant in a fluid, means the value of viscous forces are more, or simply the viscosity of fluid is more, then the flow is known as viscous flow. Another criteria also is there, that is V. It is the velocity of fluid. So if the velocity of fluid is less, then Reynolds number will be less. This velocity of the flow is less, Reynolds number will be less. So from the previous lecture we know if the value of Reynolds number is less than 2000. If the value of Reynolds number is less than 2000, then the flow is laminar flow or viscous flow. Less Reynolds number means viscous forces are dominant and flow velocities are less. So if the flow velocities are less, then also flow is known as viscous flow. Clear? Now we will set up an expression to calculate the velocity distribution inside a pipe or shear stress distribution inside a pipe. So please put down the heading shear stress distribution. Shear stress distribution for a viscous flow through a pipe. And viscous flow through pipe is also known as Hagen Poiseuille flow. Hagen Poiseuille flow. The name after the scientist Hagen and Poiseuille. So initially, in the history of fluid mechanics, it was Newton who gave the law of viscosity. But Newton rejected the effect of temperature and time on the viscosity. So due to that, after 150 years of Newton, a scientist came that is known as Navier. So Navier came, and Navier gives the equation of motion with this viscous forces. He includes the viscous force in the equation of motion. And Hagen and Poiseuille, these scientists are working on the flow of blood. The area of study for those scientists were flow of blood through veins. And as we all know that the blood is not a Newtonian fluid, it is a non-Newtonian fluid. So viscosity is not dependent upon temperature and time also. So these scientists have derived this equation. That's why this equation is known as Hagen Poiseuille equation. And this type of flow, viscous flow through pipe specifically, because they were studying on viscous flow inside a very fine diameter of pipe, very small diameter of pipe. So veins are very small diameter. So Hagen Poiseuille flow, and the equation is known as Hagen Poiseuille equation. Okay, so now we are considering a pipe. This is a pipe. Okay, at this point we are assuming that the velocity is u. Velocity u before entering the pipe. Okay, this is also known as free stream velocity. Okay. After this, it will enter into the pipe. So flow will be developed, and the direction of flow is this. Okay, the flow takes place from this direction to this direction in horizontal direction. So inside a pipe, I am considering a circular element of dx length. A circular element of this dx length, and this distance is small r. The radius of this small circular element is small r, and the radius of this complete pipe is capital R. Okay, so I am assuming this capital R radius pipe. Inside this pipe, a small element is there which has small r radius and dx length. Okay. Now, as we have already assumed, it is viscous flow. Viscous forces are dominant, means resistance will be there. Resistance will be there. Due to this resistance, shear stress will be developed. In very first unit, we have discussed this thing. Due to this phenomena of flow, viscosity, due to this viscosity, shear stresses are developed in the fluid. So there will be a shear force on this element. So shear force on this completely circular element. Suppose this circular element inside this pipe, so like this. So a shear stress will be developed in this complete surface. Now the value of shear stress will be, shear force will be shear stress multiplied by this surface area. Okay. So what will be the surface area of this? That is 2 pi r. This is, see, this is the circular element. If you cut this from this side, it will become a rectangle. If you cut this cylinder as per its length and flatten it, then it will become a rectangle. So this is dx and this is total circumference 2 pi r. So the area will be 2 pi r into dx. So the area is 2 pi r into dx and shear stress is tau. Then the shear force will be tau multiplied by 2 pi r into dx. So the shear force will act in the opposite direction of flow. So tau 2 pi r into dx. Clear? Now the next is pressure force. The flow is taking place because of pressure difference. The pressure at entry is more and the pressure at exit is less. That's why flow is moving from this to this. So flow is moving due to pressure difference. So from this side, from the entry side, pressure force is P into dA. P into dA is the pressure force from this side, and from this side pressure force will be P del P by del x dx into dA. Clear? Now if I assume the flow is uniform and steady, if the flow is uniform and steady, then this acceleration will be 0. Okay? So in fluid kinematics we have covered this thing.
Yes, sir.
Acceleration has two components, convective acceleration and local acceleration. If the flow is steady, then the local acceleration is 0. If flow is uniform, then the convective acceleration is 0. If the flow is uniform and steady both, then the total acceleration will be 0. So for this case, if the flow is uniform and laminar, the total acceleration will be 0. Okay? So now I am writing the equation of motion here. So equation of motion will be these three forces must be equal to the mass times of acceleration as per the Newton's second law of motion. So forces are, I am writing the forces. The first force is P into dA minus P plus del P over del x into dx into dA minus tau into 2 pi r dr 2 pi r dx is equal to mass times of acceleration. Now as we all know that the acceleration is 0, so this term will become 0. So P dA to P into dA cancelled out. The equation reduces into minus del P by del x into dx is equal to tau 2 pi r into dx into dA into dA is equal to tau into 2 pi r into dx. Now the area will be, for this small circular element, for this small cross section area, circular cross section area will be pi x square. So value of dA will be pi r square. So minus del P by del x into dx into pi r square is equal to tau 2 pi r dx. Okay, so dx to dx gets cancelled out, r to r cancelled out, pi to pi cancelled out. The remaining equation will be minus dp by dx is equal to 2 tau upon r. 2 tau upon r. This is the pressure gradient. LP by del x is the pressure gradient in horizontal direction, and with the negative sign means pressure is decreases in horizontal direction. So the pressure is maximum at here and pressure is decreasing in horizontal direction. This minus sign indicates, please write down, the negative sign indicates the pressure is decreasing in flow direction. The The pressure is decreasing in flow direction. Okay? So the value of tau will be from here minus R by 2. This is the value of shear stress inside a pipe at particular radius R. This is the value of shear stress at radius R. And this negative sign again, negative sign is indicating that shear force is acting in the opposite direction. Okay? The shear stress is acting in the direction opposite to the flow. Clear? Shear stress is acting in the opposite direction of the flow. Clear? Now from this, you can write it in this way also, that the tau is directly proportional to R, because just substitute the value of R is equal to 0. So R is equal to 0 means the center of the pipe. Small r is equal to 0 means the center of the pipe. So when r is equal to 0, the shear stress will become 0. Shear stress will become 0. And when you put r is equal to capital R, the value of shear stress will be maximum. Okay? So at center of the pipe, shear stress is minimum, that is 0, and at the surface of the pipe surface, shear stress, value of shear stress is maximum. So if I draw the shear stress distribution inside a pipe, so this is the center point. This is the center point. The center point value of shear stress is 0. Means the radius is equal to 0. The shear stress is also 0. As the radius increases, value of shear stress is also increases, but linearly. Okay, linearly. So linearly. And pipe surface, it is tau is equal to tau maximum. At the surface of the pipe, value of shear stress is maximum. Okay, so this thing can also be understood with the help of general understanding or general feeling. Okay, that the surface of the solid. So pipe surface is representing the solid surface and the adjacent layer of fluid. Adjacent layer of the fluid which is in contact with this solid surface having zero velocity due to highest resistance. So if the resistance is more, then the shear stress will be more. That's why the shear stress will be maximum at pipe surface and shear stress will be less into center. But the nature of this shear stress distribution is given by this equation. Okay, so with the help of this equation, we are saying that it is linear. Are you understanding? Yes. Because this thing you can clearly say with your common understanding that at center shear stress will be 0 and this is solid surface and adjacent to this the slip velocity, no slip is there. That's why the shear stress will be maximum. But what will be the nature of this shear stress? So nature of this shear stress is given by this equation. It is in linear direction. Linear nature of the shear stress. So as the radius increases, shear stress is also increases. This is the shear stress distribution inside a pipe. So everybody is clear about this?
Yes, sir. Which type of resistances we are in against of PDA?
Which type of resistance? This is a pressure difference, resistance due to pressure difference. The atmospheric difference is there, the flow friction is there, if turbulent is there, then internal resistance will be there.
So what we will be getting in and out?
Yes, that is the thing. This derivation we have covered under such assumptions. In real situations, it is not happening. There are some many more resistance are there. Internal resistance of flow are also there. Due to the velocity, mixing of layers is there. So it will we will discuss this thing in turbulent flow. Okay? After this topic, we will cover the turbulent flow, and turbulent flow we will cover this thing. So is it clear to everybody?
Yes, sir.
This is the shear stress distribution. So now the next will be velocity distribution inside the pipe. So please put down the heading velocity distribution inside a pipe. Velocity distribution inside a pipe. Should I have this? So, who will tell the Newton's law of viscosity? Newton's law of viscosity. What is the Newton's law of viscosity?
Newton's law of viscosity depends upon pressure gradient. du upon
dy is the velocity gradient, not the pressure gradient.
d theta upon dt
Is the rate of shear strain. So, Newton's law of viscosity is shear stress is directly proportional to the velocity gradient. Okay? Please now, velocity gradient. This is the Newton's law of viscosity, and the constant of proportionality is known as viscosity. So from the Newton's law we know that mu is tau equals to mu du over dy. Okay? This is du over dy. Now this y is the distance measured from the solid surface. Measured from the solid surface. So this is the solid surface. This distance is y. This distance is y from the solid surface. Clear? Now, this value of y will be, if I subtract small r from capital R, it will give the distance y. Is it clear to you?
Yes, sir.
So r, capital R minus the small r is equals to y. Capital R minus small r. Just differentiate it. So after differentiation, you will get dy is equal to capital R is a constant term because pipe diameter is constant. Diameter of pipe is constant. So r is equal to 0 minus dr. So dy is equal to minus dr. Just substitute the value. Tau is equal to mu du by minus dr. Clear? Now, from the shear stress distribution, the value of tau is minus dp by dx r by 2. Let's compare these two equations. We get minus del p by del x to r by 2 is equal to mu du by dr with minus sign. So minus del p by del x into r by 2 is equal to minus mu du by dr. Clear?
Yes, sir.
Now hand side, this equation will become du is here minus del p by del x r by 2 mu. Minus to minus also gets cancelled out. So du is equals to del p by del x into r by 2 mu into dr. Now I want to calculate the velocity. I am just integrate this equation. So with integration, du is equals to integration dt by del x r upon 2 mu dr. Except r, all terms are constant. So it will be outside in the integration. So after the integration, u 1 upon 2 mu del p by del x r square by 2 plus c, constant of integration. Integration is clear?
Yes, sir.
Now we have to determine this value of
C.
Constant of integration, and constant of integration can be determined with the help of boundary condition. So boundary condition is here. R. At r is equals to capital R, the velocity will be 0 because the surface is in contact with the solid surface is in contact with the fluid layer having 0 velocity. As per the Newton's law, this velocity must be 0. So at r is equals to capital R, this velocity will be 0. So at r is equal to r, u equal to 0, put the value and calculate the value. C is not equal to 0. So u is equal to 0 is equal to 1 by 2 mu del p by del x into r square by 2 plus c. Now c will be minus 1 by 4 mu capital R. Capital R. So 1 by 4 mu del p by del x into r square. This is the value of constant c. Now substitute this value into the main equation. U is equals to 1 by 4 mu del p by del x small r square minus 1 by 4 mu del p by del x capital R square. So 1 by 4 mu del p by del x is common. So u is equals to 1 by 4 mu so I have taken the minus sign outside so that capital R square minus R square is there. Okay? This is the velocity. This is the velocity inside a pipe. Now, the velocity must be positive. Velocity must be positive. But we have a minus sign here. So another important conclusion. So sign of del p by del s must be negative. Means pressure must decrease in the direction of flow. Only when the velocity will become positive. Is it clear to you?
Yes, sir.
In the expression of velocity we have negative sign and velocity must be positive. In the direction of flow velocity must be positive. So means this del p by del x must be negative. 0, if the r is equals to 0, the value of velocity will be minus 1 by 4 mu del v by del x capital R square, that is the maximum velocity. So maximum velocity u max, that is known as u max. So velocity u max will be 1 by 4 mu with minus sign del v by del x into capital R square. This is the maximum velocity, and maximum velocity is happening at center of the pipe. Then if the R is equal to capital R, u will become 0 and also known as u minimum. So the minimum velocity is 0 and it is at pipe surface. It is at pipe surface. Now if I draw the velocity distribution inside a pipe, so velocity is proportional to the square. Velocity is proportional to the square of the radius. It means it is an equation of parabola. So the distribution of velocity is parabolic in nature. So at center, velocity is maximum. U is maximum at center. U is equal to u max, and at surface u is equal to 0. So if you draw the velocity distribution, it will come in this way. This is parabolic in nature. Center has the maximum velocity and surface has 0 velocity. This is the velocity distribution, and velocity is proportional to the square of radius. That's why the nature of this distribution will be parabolic. So the nature of this equation will be parabolic. Okay, so with this equation we have find that center has maximum velocity, surface has 0 velocity. But if I want to calculate the net velocity for the whole pipe, then it must be an average velocity. Okay, so we need to calculate the value of average velocity now. The distribution velocity we have determined, the pattern we have determined, but if you want to calculate the total flow characteristics, then there must be an average velocity. So our next topic will be the average velocity inside a pipe. Average velocity. Average velocity. So, to calculate the average velocity, we will use this concept of discharge. We will calculate the discharge through this pipe. And you all know that the discharge is what? Area into velocity. So, discharge is equal to area of this pipe into the velocity. And this velocity must be the average velocity. Okay? So, first I am considering a small circular ring inside this pipe of dr thickness and small r radius. So the discharge through this circular ring so the discharge through small circular ring will be area is 2 pi r into dr into velocity at r. So expression for velocity is minus 1 by 4 mu del v by del x r square capital minus small r square. Okay, just integrate this equation from 0 to capital R. 0 to capital R. Integrated this equation from 0 to capital R. It will become Q, total of Q, and this 2 pi and this term comes outside. So minus 1 by 2 mu 2 to 4 divided, so 2 cancelled out, remaining is 2. So 1 by minus 1 by 2 mu pi is there. So minus pi over 2 mu and integration 0 to capital R r cube dr. Okay, this is small r we have multiplied inside this bracket. So capital R square small r minus small r cube. Now integrate this. Integrate it. Q is equal to minus 2 mu del p by del x just put the limits. So equation is reduced into minus pi by 2 mu del p by del x. Substitute the limit capital R. So R4 by 2 minus R4 by 4. Q will be minus 5 by 8 mu R to the power 4. This is the value of discharge. This is the value of discharge. Now, if the pipe radius is capital R, if the pipe radius is capital R and average velocity is u bar, okay, we are assuming that the average velocity is u bar. Okay, this bar sign represents the average velocity and area of pipe will be pi capital R square. Pi capital R square. So area of pipe is this, average velocity is this, then the discharge must be area into velocity is pi r square into u bar. So this discharge must be equal to this discharge. So just compare these two equations. So after comparison, pi r square into u bar is equal to minus pi by 8 mu del p by del x into r to the power 4. R to the power 4. So r to the power r square to r square cancelled out. Pi to pi gets cancelled out. U bar will be minus 1 by 8 mu del p by del x square. So this will be the expression for the average velocity inside the pipe. The value of average velocity will be u bar is equals to minus 1 by 8 mu del p by del x into capital R square. Average velocity inside the pipe. Yes, any doubt up to this? Is it clear?
Yes, sir.
Average velocity? Yes, the flow is Newtonian because we have derived this with the help of Newton's equation. Now, since del P by del X has negative sign, must have negative sign because pressure is decreasing in the flow direction. If the pressure is decreasing in flow direction, it means definitely the pressure energy is decreasing. Pressure energy is decreasing in flow direction means the pressure head is reduces.
Yes, sir.
Now we are calculating if the length of pipe is L, what will be the loss of pressure head inside the pipe. So we will calculate the loss of pressure head in a given length of pipe. So the next heading is loss of pressure head. The loss of pressure head in a given pipe.
And we will also assume pressure gradient as a velocity.
Velocity?
We will also assume that pressure gradient will be
The velocity must be positive. Velocity must be positive. So velocity only will be positive if the del P by del S has negative sign. And del P by del S we have already determined in the shear stress equation that del P by del S has negative sign. And negative sign indicates that the pressure is decreasing in the flow direction. Suppose this is a pipe. This is x1 distance and this is x2 distance. Okay, from this entry point, this is x1 distance, this is x2 distance, and this is capital L. So x2 minus x1 is equals to capital L. Now our focus is to determine the loss of pressure head within this length. Within this length, how much pressure head is lost, how much pressure energy is lost. So for that, we have the equation of average velocity, that is u bar is equals to minus 1 by 8 mu del P by del X into R square. So I am keeping del P one side and send all the terms into the other side of the equation. So del P is equals to minus 8 mu u bar R square into del X. Okay? I am keeping this del P on one side and send other parts of the equation to the other side. Now integrate this from 1 to 2. It will give P2 minus P1 minus 8 mu divided by r square x2 minus x1. Okay, I am taking this minus sign into this side. So this equation will become P1 minus P2. So P1 minus P2 is equal to 8 mu u bar r square, and x2 minus x1 I can replace it by capital L. So capital L, 8 mu u bar L divided by r square. Now in diameter form, also you can write in diameter form, the radius is d by 2, half of the diameter. Just put the head. So P1 minus P2 is equal to 8 mu u bar divided by d square by 4. D square by 4 into L. Now divide this equation by rho g. Divide this complete equation by rho g. So P1 minus P2 divided by rho g is equal to 32 mu u bar L divided by rho g d square.